surface of degree D and dimension n, defined by polynomial f. So we know hypersurfaces consists of three basic types of varieties: follow variety, Carl and genotype. And even though the defining way of hypersurface are simple, just one equation, but the geometry and properties are rich, related to many interesting problems like rationality problem and mirror symmetry and so on. So, and automorphism group is a invariant of variety. So we want to know the automorphism group of the hypersurfaces. Also, because it's a hypersurface, it's the automorphism which preserve the hypersurface. So that's in general, it's a subgroup of the full automorphism group of the hypersurface. We denote this subgroup linear part Ln, and this subgroup is an algebraic group with finite many components. And in 1963, and Mashmura-Mansky proved that if n greater or equal to 2, d is greater or equal to 3, but nd latter equals to 4, means latter the quartic case-to-case, then the automorphism groups of the hypersurface X is actually equal to the linear automorphism of X. Moreover, this group is actually finite. It's essentially just due to the fact that because hypersurface is by Lefschetz hyperplane section theorem, so the Picard is either Z in the dimension greater to 3 case, or in that case, because any automorphism preserves then preserves the O of 1, the generator. And in surface case, because we have the O of 1 is multiple of O of 1 is canonical line bundle, so and also preserved. You can easily see this equality. And finite group, because the dimension is 0, the automorphism group dimension is 0. And in the plane curve case, Chang in 1978 also showed a similar result for degree greater or equal to 4. The argument is slightly different, but okay. So that means in the hypersurface case, except the elliptic curve and quartic case-to-case, so the classification of all possible groups of automorphism is equivalent to the following projective linear algebra problem in classical invariant theory. So the problem is just to find all possible finite subgroups G inside the PGL. Of course, the PGL is just the automorphism group of the projective space. So such that there is a homogeneous polynomial F, which of degree D, and which is smooth, such that the finite group G preserve the polynomial F. So then it's like essentially it's just a linear algebra problem, but so in practice, so in principle it's can be done, but in practice there are some difficulty. So the main result today is the following. Automorphism group threefold, and so we have the, if for finite group G, if it acts on some, it is a subgroup of one of the 22 groups listed here. So we also provided the generators of those 22 groups, and we also give the explicit hypersurface which act on And this classification, the classification is inspired by Mukai's classification of finite groups of symmetric actions on K3 surfaces. And in our case here, the finite group G, in quantic case, the order always divides this big number. For instance, all possible prime factors of the group G is 2, 3, 5, 13, 17, 41. And the maximum possible order of the group is this 75,000, which act on the Fermat. Moreover, group theoretically interesting thing is one know which kind of long abelian simple group could act on the quantic threefold. It turns out only one. So the quantic case examples. So some are, of course, low and before example like Fermat and some other like polynomial are very simple, like just 5 monomials. That's easy to construct. But there are some examples we couldn't find in the literature. So we find some new examples in the process of classification. Okay, so in the cubic threefold case, the possible group are much fewer. So it turns out a finite group can act on a smooth cubic threefold if and only if it is isomorphic to one of the following 6 groups. Every possible G, the order divided this number. So for instance, all possible prime factors are 2, 3, 5, 11. And the maximum order is 9,720. So this, again, this is Fermat. And for non-abelian simple group, just two possibilities, A5, and another one is the PSL211. So here, 2 means entry the finite field with 11 elements. So this group P is quite special, and actually this group cannot be embedded into the criminal group of rank 3, and by result of Pruckner. So it's kind of explanation of this PSL acting on the Klein quartic, Klein cubic threefold. So it's kind of explanation of the non-rationality of this cubic threefold. Of course, we know by result of Clemens-Griffiths, every cubic threefold, smooth one, not rational. Okay, so the explicit examples are also given, and some examples we find from the classical works, like the second one, we find the example from the literature, but add just 2 more variables, x4 and x5. Okay, so then I would like to explain the main ideas of the classification. So first of all, how we want to know, the one important thing is how to use smoothness condition. We actually check smoothness method in proposition, like so if you have a cubic or quantic threefold, actually you have any like threefold, smooth threefold of degree greater or equal to 3, then x is singular if one of the following 3 conditions is true. So it's combinatorial. So for instance, the second one is say that if you have two variables such that the polynomial is inside the idea generated by those two variables, then f is singular. So this actually have geometric meaning because that means the hypersurface contain a plane, but this is impossible for smooth threefold hypersurface. So these three conditions, the good thing is you can use the computer handle effectively. So for example, let me just quickly explain how to apply this computorial smooth test. Suppose you have finite many matrices, invertible matrices, A1 up to A. We want the that all those AI preserve this F. First step, you just compute the set of all monomials invariant by those matrices. So then, of course, since F is preserved by all those AI, then F must be of the form like this. So it's a summation with coefficients. And in this, at this point, we don't directly apply the Jacobian criterion because could be time consuming. You take all partial derivatives and try to find the common zero. Instead of that, we just apply the proposition just mentioned, those three conditions. So often we can rule out F, or if we cannot rule out F, that means the proposition fails, then we just try to find actually smooth, find the existence, so find the explicit smooth F with suitable the coefficients. Sometimes we could get a uniqueness of this smooth F. So this is how to use the combinatorial test. And example, more explicit example, like for example, you have A is diagonal of order 2. The first three entries are -1, and the last two, the first one is ±1, the last one is 1. Suppose you have a polynomial f and of degrees 3 or 5, and if you know AF is equal to F, so AF means just you do linear change of coordinates. So then by this one, we know this F must in the idea generated by x4 and 5, because the total degree is 3 or 4, 5 is odd number, and the first three coordinates are -1. So you must every invariant monomial should have x4 or 5, and then the hypersurface is singular. So that's kind of how to rule out. This is a simple case. Could be more complicated, like order 9 case, or could be you have more than one matrices. Then you want to compute all invariant monomials and decide whether can apply the proposition or not. Then we just use computer. Okay, so this is smoothness condition. Another thing is we want to reduce the classification of finite groups in PGL to GL5, because in PGL you have some complicated kind of complicated, because this is two matrices could represent same. So we want to go to the use the linear representation theory of finite groups, look at the character tables and so on. So then to do that, we just introduce this so-called F lifting. So the definition is just like the following. So suppose you have a finite group of the PGL, and you have a polynomial f. So we say the group G is f-liftable if G admit lifting G tilde to the GL, and moreover, AF equals F for all A in this G tilde. Then we say this G tilde is actually an F lifting of G, and in other words, the G is F liftable. So that's F lifting. So the critical part is here for the lifting all the coefficients. Here is AF is equal to F, low constant multiple here. Okay. So at a special case, an element finite order in PGL have F lifting if H equals some capital H represented by some of capital H generated by So the group generated by capital H is an F lifting of the group generated by small h. Okay, so let's say example why the action in general not F liftable. Let's look at the middle one. In this case, the Fermat quantic, and you look at the group G, which generated by the following two matrices. The first A3 is just a permutation of the 5 coordinates of order 5. So that means you replace x1 by x2 and replace x2 by x3 and so on. And A4 is the diagonal matrices with trace 0. So you can easily check these two generate a C5 square in PGL. This means this abelian group of order 25 and C5 cross C5. And but in the GL, it has low lifting because it's not commute in the GL, so low lifting. So then surely no F lifting. So this shows some complicated aspect. Yeah. So to treat the F liftable, we prove the following. Suppose you have G is some finite group of PGL, and you have a polynomial F of degree P, which is a prime number. In our case, like quantic and cubic is fine. So suppose F is G invariant. In other words, this G act on the hypersurface defined by F. And let the GP is just a cellular P subgroup of the G. Then the G is F liftable if the following two conditions are satisfied. First one is the GP is F liftable. And the second one is either GP has low element of order P square, or G has low normal subgroup of index P. In the quantic case, for example, in the quantic case, it turns out no automorphism of order 25. So that means the second condition is always satisfied in a quantic case. So we only need to check F liftability for cellular 5 part. So that's the following. So a G in the order of quantic threefold if then G F liftable if and only if the cellular 5 part is F liftable. By that, so luckily, so many possible liftable. It's actually simpler. We show that for smooth cubic threefold, then always F liftable. So group G. One remark is very recently, the following generalization is announced by them. So suppose n is greater or equal to 1 and d greater to 3, and d is not 1, 3, 2, 4. Then the automorphism group of every smooth hypersurface of dimension n and degree d in Pn plus 1 is F-liftable if and only if the d and n plus 2 are relatively prime. So for example, in cubic case, d is just 3 and 3, so 3 and 5 are relatively prime. So this is a consequence then. And in the quantile case, d is 5, n is 3 plus 2 is 5, so not relatively prime. So there are non-liftable F-liftable ones. Okay. So now by F-lifting, for example, then this table is like we classify all abelian groups, abelian because and all possible F-liftings. For example, here, but here, in this table is just the order of H is less than or equal to 9. In our classification, we actually can determine all possible abelian, but the table is longer, so just put this part. For instance, for the order 2 element, the trace, it's like that after diagonalization, it's like this, -1, and the second one is either -1 or +1. The remaining is +1. And for example, say for the order 4 elements, you must have eigenvalue is -1. So, moreover, some cases we can decide the hypersurface uniquely. So, like for example, if we say an order 9 automorphism acting on smooth cubic threefold, then the smooth cubic threefold must be isomorphic to the Fermat. So rigid this action. And of course, this is just again, this is just a combination of with F-lifting and then use smoothness, and then you get this table. And I would like to give an explicit example, like how to use F-liftability and the smoothness and the character table to rule out the quaternion group Q order 8, Q8. In other words, it cannot act on any smooth cubic threefold. So of course, the linear representation theory of Q8 is very known, and actually, so this is a table. So it have 5 conjugates classes. The first one is order 1 element, and have 3 order 4 conjugates classes, and have only 1 order 2. And now suppose otherwise Q8 can act on some cubic threefold, then by our theorem, there is a F-lifting that say G tilde in GL5. That, of course, corresponding to a 5-dimensional faithful linear representation, say chi, of the group Q8. Then divided into 2 cases. The first case is chi5, the 2-dimensional irreducible representation, plus the remaining IJK. IJK are 1-dimensional irreducible representations. Or case B is you have 2 times chi5 and plus 1 remaining one is 1-dimensional. Chi5 must be involved because Q8 is a non-abelian group. Okay. The case B, because the 2A, the order 2 element, the trace 2 times that 1, it becomes -3, then contradicts to your classification here, order 2 element. So case B is impossible. Now case case A. Case A, then you a little more complicated. So then you have 3 non-trivial one-dimensional irreducible character like this. Then by number 5, by order 4 element, always have at least 1 minus 1 as an eigenvalue. So that means for 4A, -1 must appear once inside this IJK. And also 4B, the -1 must appear at least once. Similarly, 4C. Then it turns out whatever you choose IJK, it turns out your trace of this 4A, 4B, 4C, one of them must be -1 or -3. That's impossible by the classification of in the table before, because the trace cannot be -1 or -4. That's the rule out. So A, impossible. This just finished the proof of impossibility of Q8. This actually used many times in the quintic case and in the cubic case, because you have F-niftybility. You can use the Carrot table, and then use the smooth classification. This is kind of local information, because the abelian part is easy to classify. It's like you have lots of constraints on the eigenvalues. So then you can look at those ones. So this you combine global information and the local constraints, then you rule out many cases. Okay, so this is F-liftability. So another thing is for given hypersurface like Fermat or Klein, so if the number of monomials are very few, then it is possible to directly compute the full automorphism group. In other words, you decide all possible linear transformation which preserve the polynomial. It turns out in the quintic case, we can use the so-called differential method to do that. Let me explain the notation a little. So suppose you have F is a polynomial of degree D, and naturally you have the following evaluation map. This one is the vector space of S order S order differential operator, like take partials, and the domain is just the polynomial ring. So this I denote the subscript I is just the S partial derivative, and the order of, so 1 means you take a 1 partial derivative, 2 means you take a double partial derivative. F is just you apply to a specific given polynomial like this. So of course this is a linear map. Then you can define the rank of the image space. So this kind of rank with given F. So now our result is, suppose you have another polynomial G in some other coordinates variables like y1 up to yn. Sorry, here G is not a group, it's just some other polynomial. Sorry for the bad notation here, but temporarily use this. So if F and equals G under certain invertible linear change of coordinates, in other words, suppose you have some matrices L, and such that F equals G after this change of coordinates, then we just have this rank of this DIF equals rank of DIG for all essentially it's just that means the rank of some invariants of the polynomial, which invariant under the linear change of coordinates, put in other words. So let me explain how to actually use this in a concrete case. For example, let's take the Klein quintic threefold, means this one. Of course, the monomial, only 5 monomials. So we want to know whether all interchangeable of coordinates preserve that is like a permutation or diagonal action or composition of those kind of. So if we can show that, we just find all possible automorphism of Klein. To do that, suppose after you have invertible matrices L, and you do linear change of coordinates, and you put yi the resulting coordinates, and then you have those two equal because they preserve the polynomial. And then you apply the partial x1 to both sides. Of course, by chain rule, you have this identity. The left hand side, you just take the partial derivative x. Hand side, by chain rule, you get this long polynomial in variables y. Note the side by this small h, the new polynomial in variables y1 up to y5. Of course, you can easily compute this rank. The left-hand side is just 3 because you just take one more partial derivative of this again. The image space is just 3-dimensional. Then by the theorem just mentioned, we know this rank must be equal to 3 also. So from that, then you do a little more computation, show that the L11, L21, L351, 31 up to L51, exactly one of those 5 numbers is not equal to 0. So that means the first column of this invertible matrices have exactly one non-zero entry. Then by symmetry, you can do the same argument, same kind of argument. By symmetry, other columns also have this kind of property. Then because the L is invertible, so that means L is just like permutation is of the shape we want. So that's how you prove that. So and actually, this differential method is inspired by Poon's work on hypersurfaces without long trivial automorphisms. And we know a general fact for smooth hypersurface, for generic one, automorphism group is trivial. And of course, it be of interest, you give explicitly relatively simple examples of hypersurface such that automorphism group is trivial. So Poon actually give explicit examples quite simple, like this. First one is taken. His formulation is more general, up to D and N and characteristic free something. We just take in our case the quintic over number C. So this polynomial you easily check by Jacobian test is smooth, and it have only 6 monomials, and then we can apply the differential method just mentioned to show that the automorphism group of this hypersurface is actually trivial. So yeah, and his argument, of course, is not the same as ours, but from his argument, we just formulate and kind of a variation of our formulation, a variation, and of his and different. And inspired by that, we can give some threefold, which are smooth and defining equation relatively simple, but the full automorphism group is quite small, like C2, this one, with just 6 monomials. You can easily check this act, and then by differential method, this has to be only automorphism, non-trivial automorphism, and so on. Okay. So this is the differential method. So the differential method, the idea to use this is like often, for example, you have a big abelian group acting on like a quantic, then you compute the invariant monomials, and you end up with a unique quantic threefold, and then you want to control the full automorphism group, then we just use the differential method, and then we essentially control all possible group contain this big abelian group. Okay, so another thing is we use some result in linear representation theory of finite groups. Let me first record the result by prove that for the Klein cubic threefold, the full automorphism finite PSL to 11. And actually, this have some history. As you can see, the name of the cubic Klein actually give the action PSL to 11 acting on this one. Adler, he shows that actually this is a full automorphism group. So how did he do that? He used the following theorem of Brouwer. So for you, if you have P is some prime number and you have G is a finite group such that the zero P is just a cyclic group of order P, and the finite group GP, the zero P part is not normal, then if G has some physical representation in degree P minus 1 divided by 2, then the quotient group of G modulo the center is isomorphic to the PSL to P. In Klein case, just apply P equals 11. And he actually have need one more ingredient is from PSL is the same as PGL, from PSL to SL. So in this case, because the rank is 5, so this one is cyclic of order C5. So relative prime 11. So this central extension doesn't matter. So still can apply the Brouwer theorem. And then of course need some more computation to show that actually can apply this. Then he shows that this is a full automorphism group. Inspired by that, we want to, in the quantic case, we want to control the automorphism group of quantic threefold in the case primes 13, 17, 14, 41. This large prime divide the order of the automorphism group. And in that case, we actually prove that the zero P part is actually normal. It's kind of opposite way to use the because in Adele case, Klein that's a simple group, and in other cases it's normal. We actually apply a larger, quite closely related to Brouwer theorem. This is all very similar. So GP is CP. This part we can compute we decided the zero p part is CP. The question is where is normal or not. Then if the biosystem, if it's not normal, then any degree smaller than divided by 2. So for example, 13 minus 1 divided by 2 is 6. And then we use similar this exact circuit again. It goes to SL, and because 5 is less than 6, so end up with must be normal. So this with this normality, and then with this normality, then because it's kind of roughly speaking, it's kind of you can, it's like a Abelian case. You can control the remaining automorphism. Okay, so for cubic case, how to treat the case involve large primes? Yeah, actually, this is just a quantum case I just mentioned. The cubic case, the large prime is 11. So in this case, fortunately, we have the following result. So we can use this one. So if 11 divided the automorphism order of the automorphism some smooth cubic threefold, then X must be isomorphic to the Klein cubic threefold. So that means we don't need, and we know the full automorphism group is PSL 211. So if 11 involved, then we don't need to worry. By the way, this Klein cubic threefold case generalized by them like as follows: if n is greater or equal to 2, and if the cube smooth admits automorphism of prime order p greater than 2 to the nth power, then the x n3 must be isomorphic to Klein cubic n-fold. This generalization. This yeah. Okay. So now the remaining problem is to treat the cases, the group, the final group with order only involves the small primes, like 2 to the power A, 3 to the power B, 5 to the power C. So for such kind of group, there are many candidates, too many. So almost impossible just by computation by hand, almost impossible. So we use the computer algebra system gap extensively in both cases. So the gap is just the name. The full name is groups, algorithm, and programming. So this algebra system is actually a kind of special design for group theoretical computation, many useful functions. So in our case, we use the following function of the computer system gap. Suppose you have some positive integer m is less than or equal to 2000, but m is not equal to 2 to the 10th. This is 1024. Then gap can do the following things. First one is just give a list of all finite groups, of course, up to isomorphism of order m. Also can do give a list of all possible, all subgroups of any given group G with this order m. And moreover, it can also give all normal subgroups. Certainly can give the character table of G, and also can give structure description, like whether it's like a permutation or it's alternating, or it's cyclic, or direct product, or semi-direct product, and so on. For this is less than 2,000. For non-abelian, sample group can do more for more larger order, like for example, less than 1 million, they can give list of all possible or sample groups. And more functions we use. Mostly we use this in our classification. So, and with those functions in hand, actually we can do the so-called subtest using gap. What does that mean? So we want to consider the set of all finite groups G such that it can act on some smooth X and D, and the G order is M. Suppose the set G1 up to Gn minus 1, M minus 1 are all determinant. Then next we determine the Gm where we by the following steps. The first we rule out all finite groups G of order M such that it contains some proper subgroup which not act on any smooth X. Then ruled out. And second step, if G survive in step 1 means cannot rule out, then if it's already reliable by known examples, then we don't need to worry. We just put that in the list GM. If for other ones, undecided G after steps 1 and 2, then we do case by case check. And that means like we look at the character tables, and we look at the abelian subgroups, and we look at the some other information to decide. If we either rule out by some group theoretical or linear repetition way, or we find actually a new example. So that's the idea. Quantic and cubic 3 cases, this subtest turns out to be effective. Means the effective means in step 3 there are not too many groups near to case by case check. Okay, this is the computer program gap. And of course, when you try to produce new examples, then we use the Mathematica to check smoothness, because then it could be end up with a new example with a complicated defining equation. Then we use Mathematica. Of course, not necessarily Mathematica. You can use some other computer programs. Can do. But computer is more efficient. Okay, so now how about the cases order greater than 2,000? We just says if order is less than 2,000, we can use the gap. But how about greater than 2,000? In quantic and cubic case, turns out we can reduce this larger order cases to smaller order cases, means less than or equal to 2,000 in computer-free way. And for example, for solvable group G, if your order is like equals this is equal to M times K, and MK is relative prime, then you have subgroup of order M, and any two subgroup of order M are conjugate, and any subgroup of order divides M is contained in a subgroup of order M. So this is kind of generalization of Ceylon groups. But if it's solvable, then it's have this kind of formation. Of course, this result is very known in group theory, so we just use that useful. And for non-solvable group, for example, we can consider the following exact sequence. So for non-solvable group with order greater than 2000, we let the N is the maximal proper normal subgroup of G, and M is just a quotient. By choice of this capital N, the M is a finite simple group. And we know the classification of finite simple group. So then we have good controlling. And then in both quantic cubic cases, it turns out we can use this handle or large order cases. And so to summarize, the strategy is like following for fixed N and D to classify all possible G. We roughly proceed the following steps. So first, determine all possible prime orders. First, the secondly, which I will explain later how to do step one. And step two is determine all possible abelian groups and classify all possible F-liftings. And the third one is just determine all possible C or P, and then all possible solvable of order less than or equal to 2000, and then solvable group greater than 2000, and non-solvable, and so on. So after the step 7, then we're done. So for the first step, it actually can be handled by this one. Suppose we have some primary number Q equals P to the power K, then such that this Q is relatively prime to D and D minus 1. Then Q is the order of an automorphism of some smooth hypersurface of dimension D, dimension N and degree D, if and only if there exists an integer L between 1 and n plus 2, such that it satisfies this 1 minus D to the L's power equals 1 modulo Q. So how to apply this? So for ND equals 3, 5, quantic case, you just compute the 5 numbers, L equal between 1 and 5, so 5, and you get a factorization. So from that and this theorem, you get all possible primary orders for quantic case are 2 to some power A, and 3, and 5 to some power, and 13, 70, 41. 2 and 5 were not treated here because not satisfy this one in quantic case. But certainly for any prime divided D and D minus 1 can act. For example, if a prime divided D, then you can act on the Fermat. For D minus 1, you can act on like x1 to the D minus 1 times x2 plus x2 to the D, and plus remaining just like Fermat kind. So in other words, all possible prime factors can be easily handled. Actually, very recently, a method to determine all possible orders, not just primary, all possible orders, means actually cyclic groups. For any smooth X in dimension n, given dimension n and degree D, he had a method to determine all possible orders, announced by Zhen. The idea is to look at all those polynomials with very few monomials like Fermat and Klein and those kind, and he computed all like a diagonal actions for those kind of polynomials. So determine all possible order. Okay, so then how about this is our classification for in the quantic threefold and cubic threefold. How about for other n and d? And there are actually, to my knowledge, mostly towards the classification of automorphism group, mostly many works in plane curves case, and plane and cubic hypersurfaces. Like for example, cubic, the all possible automorphism group of cubic surface is classified. And for higher dimension, like cubic fourfold, and for for example, symplectic one recently classified by Laza and Zheng. But the full automorphism group classification seems unknown in that case. For other for other cases, not so many known results seems for classification of auto X and D. Hopefully, our strategy can be applied to new pairs of ND. And just a few more minutes, and let me explain application of the classification of quantic automorphism quantic threefold. We know it is an open problem, and how many different topological types of Calabi-Yau threefold have. This turns out to be very hard, and related problem is which kind of pairs of integers can appear as the pair of Hardy numbers H11 and H21 of Calabi-Yau threefold. Even boundedness is still unknown for projective Calabi-Yau threefold. And list of known Calabi-Yau threefold is huge. For example, Kuzer-Skarke list, so many different Hodge pairs. So this makes things difficult. It's like hard to predict what kind of patterns or rules should follow by the high numbers of Calabi-Yau threefold. And related thing is so-called Markov correspondence can provide a way to construct a Calabi-Yau threefold. Suppose you have some given Calabi-Yau threefold have a finite group acting on X constantly, means preserve the non-zero holomorphic three form omega. Then you consider the quotient variety, and then you consider the Querpen resolution, which always exists. And the Querpen resolution is again a Calabi-Yau threefold. It could happen that some new Calabi-Yau threefold will appear in this way. And a very famous example in biosymmetry is you have diagonal action, the C5
For the cubic case, it's not the unique one.
Cubic case, if order is maximal, also unique.
Oh.
The hypersurface, yes.
Okay, but in a quartic case,
quartic, you mean? For Feynman, I guess for Feynman.
Yeah, I remember for surface.
But for quartic, of course, for quartic K3, the automorphism, full automorphism are actually infinite. But for finite symmetry, actually, it's a result of Grisel says that the linear automorphism of Feynman quartic K3 from P3 actually determine the Feynman uniquely among the K3 surfaces.
Okay. Thank you.
Yeah. Thank you.
Yeah. Some more questions? Okay, then let's take a 10 minutes break. Okay. Thanks again, Professor Yu.